recording is up. And I'm going to mute myself and start the broadcast. For everyone online, I'm starting the broadcast.
Okay.
Murad, you could maybe say a couple of things, just invite people and say that we'll start in 10 minutes.
You mean as a chat?
No, not on the chat, on the broadcast. As soon as the broadcast comes up, people will start joining. So before the session starts, you can just welcome.
Okay, I'll mention that we are starting in 10 minutes. Okay, please.
Yes. Hello. Good morning, everyone, or good afternoon, or good evening from wherever you are listening from. Welcome to ICDE 2020. Today is the third day of the conference, actually second day of the main conference. And I'm Bhavani Thuraisingam, the general co-chair of the conference. And we just finished the sponsor presentations. That is from Alibaba, our gold sponsor that was just completed this morning. And then this evening from 4 to 5 p.m., University of Texas at Dallas, our platinum sponsor, they will be giving a presentation that's after the conference. So all the times are Central Daylight Time in the United States. So that will be from 4 to 5 p.m. And then tomorrow morning, from 7 to 8 a.m. in the morning, again, Central Daylight Time, we will have the sponsor presentation, gold sponsor presentation from the Qatar Computing Research Institute. And so, again, welcome to ICDE 2020, and we have 2 more days to go. Tomorrow is the last day of the main conference, and Friday, we are going to have WIDS, Women in Data Science Day, as an ambassador to Stanford University's Women in Data Science initiative. So at this time, I'm going to hand it over to one of the research PC co-chairs, Dr. Murad Kantarzoglu, to introduce our keynote speaker. Thank you.
Also, please mute your camera. Okay. Good morning, good afternoon, and good evening. This is Murad Kantarzoglu. I'm PC Research Co-Chair with Sudarshan and Dimitrios. So it's a great pleasure to introduce Joe Hellerstein for the third keynote of the conference. Joe is the Jim Gray Professor of Computer Science at the University of California, Berkeley. His research focuses on data-centric systems and the way they drive computing. He is an ACM Fellow, Sloan Research Fellow, and the recipient of 3 ACM Sigma Test Time Awards. Fortune magazine included him in their list of 50 smartest people in tech, and MIT Technology Review included his research as in the list of 10 technologies most likely to change our world. In addition to all these academic achievements, he is the co-founder and the CSO of Trifecta, which brought academic research on data wrangling to the market. In addition to all these achievements, he is an amateur jazz trumpet player and has performed at notable venues including Yoshi's ICD and VLDB. So I guess let's virtual welcome to Joe for this keynote. Joe, please start.
Hi all, Joe Hellerstein zooming in from Berkeley and this recorded talk. A real honor to have been asked to give a keynote this year at Data Engineering and to be able to give it despite the challenges that we have. It's unfortunate we can't all be together and have the hallway conversations that make conferences what they are, but at least some of us are getting together here and going to have some conversation online after the video. So thanks for having me. It's an honor. Today I will be talking about a data-centric lens on cloud programming and serverless computing. It's a talk in 4 chapters. I'll start by giving some background on what's going on with serverless computing today, at some of its potentials and limitations, and thinking about it as a first step in the ability for us to really program the cloud. Then I'll step back and talk about some research that's been going on for some time in my group on avoiding coordination, which is one of the most expensive aspects of working with cloud scale systems, particularly data systems, and the theoretical result that underpinned a lot of that work, which is the Calm theorem. And I'll go through that for folks so you can understand kind of the foundations of this stuff. And then with that background, talk about where we're going next, talking about how to take serverless computing and make it stateful and handle data, and then how we go beyond that to a more general notion of cloud programming. And I'll talk about a system we're building at Berkeley called Hydro to explore some of these ideas. So, you know, it's useful to go back and think about the various platforms that have been developed over time in computing. You know, go back at least as far as the mini computer, MP11, early 1970s, late 1960s, going through supercomputers, personal computers, and smartphones. Each one of these platforms leading to a real revolution in the class of applications that we were able to do with computing. And there's a sort of common trope that's echoed often in the systems community, that with a new platform comes a new programming language or a new programming paradigm that enables developers to build applications you never would have expected on these platforms. So this story goes very much comes from the Unix community and the combination of Unix C and the PDP-11 being this environment that was well suited. All the pieces kind of fit together properly to give a platform for people to do things that the developers of the system did not expect. Supercomputers had similar new programming paradigms, and then when we got to graphical user interfaces in the Macintosh in particular, applications like HyperCard led to what we think of as the web today, and applications like LabVIEW led to drag and drop graphical programming, so new paradigms for programming visually. And then of course with the smartphone now, there's an app for that, right? And the platforms that we've built for smartphones have led to applications that really the developers of the smartphones never could have imagined. So key to all of these new computing revolutions is the idea of a new language or programming model leading to innovation outside of the core engineering of the platform. Now, one of the big questions I think in computing today is the cloud is the new platform other than the cell phone that's been invented in the last decade or so. And we still haven't really answered the question of how will folks program the cloud in a way that fosters unexpected innovation by third parties. So developers inside of Google and Amazon obviously are writing software. It's not to say that it can't be done, but there's not a lot of third-party software being written outside of the cloud vendors that is surprising and innovative and takes advantage of the novelty of the platform. Because when you think about the cloud, what is it that's different from other platforms? It is the biggest computer we've ever delivered as a race, as the human race, right? It's got more compute, more storage, and more geo-distribution than anything that's ever been built. And somehow most of what we've built on it is just respins of things we already had in the data center. So databases and application servers and web servers and so on. Very little, platform novelty coming from third parties as of now. So how are we going to build that programming model that's going to foster that creative innovation so that there'll be an app for that is cloud scale? Well, part of the problem is that building a programming model for the cloud's really hard. Distributed programming is hard. It's got all the challenges we had with supercomputers of parallelism, but it also has these issues of replicated data and consistency and partial failure of components of the system, which is what makes replication so difficult, right, in distributed systems. And then unique to the cloud, particularly recently, is the idea that the systems should be elastic and auto-scale up and down with workload. That makes it only harder because as you add and remove computers to a computation, it's very much like failure of nodes. And so that's a sort of managed failure, but it's still tricky to handle. All right, so these are all things that make programming the cloud hard. Now, I've been talking about this, honestly, for over a decade, since not long after AWS was launched, that this is going to be one of the key problems for computer science, and particularly for the data-centric aspects of computer science for our community. And certainly we got attention for this. I've had 2 generations of really brilliant graduate students working with me on some of these problems over a decade, and yet still I'd say we haven't reached answers on this, and certainly we haven't reached answers in the broad computing community. We generated a lot of ideas in our group, but things haven't really caught on in wide usage. But what we're seeing with the industry today is finally they're starting to wake up to this idea that there are developers outside of the cloud vendors themselves who could be programming the cloud. And this is being promoted right now under the guise of serverless computing. So I don't know if you're susceptible to marketing, but serverless computing is now nearly as popular as MapReduce was at its peak in terms of Google Trends, and has certainly surpassed MapReduce currently as the hotness. So people are talking a lot about it. Whether or not it's got content is something we'll talk about. But it is something that's on people's mind, is this idea that programmers should be able to put code in the cloud without thinking about launching and maintaining servers. And the cloud vendors should be able to execute that code whenever it gets invoked by a client. So let me give you a little background on what serverless looks like today in terms of the offerings for third-party programmers from the cloud vendors. So when they say serverless today in their marketing outbound to programmers, what they're talking about is what's called functions as a service, or Faas. And these are services where you can upload a function written in Python or Java or JavaScript, your favorite language, and have that function be invocable through a REST endpoint or some other network endpoint, and execute and then go away. And this enables the developers outside of the cloud vendors to, in some sense, program the cloud and get the advantage of the scalable platform with a simple and familiar programming model. And the key with this is that it's fine-grained resource usage and efficiency. So if your function is run 1,000,000 times, you'll pay for 1,000,000 usages. If your function is run for 0 times, you'll pay for 0 usage. So there's no reservation of nodes, and there's this very fine-grained accounting of the resources that you consume. And this enables, of course, new economics, new pricing models. And there's a belief both on the cloud vendor side and on the customer side that this is mutually advantageous. So serverless computing does deliver on at least one of the promises of the cloud, which is this notion of auto-scaling. Serverless computing finally really offers this. So now I can have a function that will scale up and scale down in short amounts of time without me thinking about that. But it's also been 2 steps back. And we wrote a paper about this at CIDR last year, where we pointed out that 2 of the key things that you would expect out of the cloud are actually stymied by serverless functions as a service. One is massive data processing. So actually you cannot get efficient low latency access to all that storage in the cloud. And the other is unbounded distributed computation. You also cannot write a massively scaled distributed application using serverless computing. So let me talk about both of those in detail. But the high-level message is we've got a platform that's got all the storage in the world and all the cores in the world, and it won't let you get efficient access to the storage, and it won't let you synchronize those cores to do distributed computation. And so in some sense, it's super frustrating, right? It's exactly the wrong fit for this exciting platform, which is the cloud. So the key limitations of current functions as a service offerings, and I'm going to pick on AWS Lambda mostly because it's the largest and the most popular. It's the one I'm the most familiar with, but the Google and Microsoft offerings are quite similar. Significant bottlenecks for I/O, so latency in particular, 10 to 100 times slower than an SSD. Moreover, you pay in dollars every time you do an I/O to serverless storage system like AWS S3 or DynamoDB, which are their serverless offerings for storage. You pay dollars every time you do an I/O. So you really can't do a lot of low latency I/O. You can't have a fine-grained I/O pattern in a serverless function. It's just too expensive in both time and dollars. Serverless functions have bounded lifetimes, and this is part of the philosophy of it being serverless, is that you shouldn't run servers. Okay, so your function should complete in a reasonable amount of time. Now, if you actually want to run computations that are long-running or that offer services, those functions will fail every 15 minutes or so, which means that failure is going to happen quite often. Mean time to failure, only 15 minutes for your components of your system. So you really can't assume that if you've connected to a function in the cloud, that if you reconnect it, it will remember who you are or remember anything about you. You really can't assume any session context. Part of that's because of the lifetimes, and part of that also is because the I/O of remembering you is too expensive. And then the last and arguably the most frustrating, because it doesn't have to be this way, is that cloud functions are not allowed to have inbound network communication. So two cloud functions can't talk to each other. Two Lambdas can't talk to each other. So you can't do distributed computing. The only way for Lambdas to talk to each other is to use the shared medium of storage. So one Lambda can write to a well-known location, another Lambda can read from that location, but again, very high latency, very expensive. Okay, so you can't really have chatty protocols that do distributed computing. Still, I think serverless, it opens up a conversation that I've been waiting since at least 2010 to have about how will we program the cloud. And it's a baby step, I would argue. It's really simple. You just run simple stateless functions in the cloud, and it allows you to do some stuff. And people have been writing papers about, hey, look, I was able to do a big parallel map job in the cloud, and with that, I can do certain linear algebra operator. That's great, and that's nice. And so, I think sometimes in research we want to look really far out and do ambitious things. And sometimes the way that gets adopted in industry is to take smaller, more easily engineered steps to answer these big questions. And so timescales here are really long. We're talking about decades, but we're beginning to now make those small steps and open the conversation about the big question in a broader context. Okay, so summing up the first chapter of this little talk, serverless computing, one step forward on autoscaling, 2 steps back on latency-sensitive data access and distributed computing. So that gives you a sense of where we are with serverless computing. And the next thing we'll talk about then is to step back and talk about what it means to avoid coordination. So as a first step to go beyond the state of functions as a service today, what we really want to do is have them be not stateless functions that can't have anything that they remember, but stateful functions. We want to embrace the notion that functions have state. They have the state of their variables or the state of a database, and that program state, that local data, should be persistent across invocations. So when you call a function and then you call that service again, it'll remember something about you, which is pretty important. Most interactions with hosted services are not single interactions, they're repeated interactions. So this raises at least 2 challenges. How do we manage state in these functions in a massively distributed system? The first challenge is a performance challenge, and it's one that we're all familiar with in data engineering, right? Which is data gravity. It's expensive to move state around. The second challenge is the thornier one, the harder one, which is distributed consistency. So this is a long-standing hard problem in computer science, and especially in the database community. It's a correctness problem. So it's difficult, it's unavoidable. You have to solve this problem. And it's not solved incrementally through agile engineering of ironing out performance bottlenecks. This is something that you have to get right. And the challenge with consistency, to remind us all, is that distant agents would like to agree, or at least you'd like them in eventuality to agree, on common knowledge. So we have our friends here on the upper right, and although they're in different time zones, one's looking at the moon, one's looking at the sun, they agree that x equals love. Right? And so this is a classic example of data replication. X is a variable, and we want to know that they agree on the value of that mutable variable x. So the problem that arises is when they can't communicate for some reason. There's a partition in the network, and the state of the variable changes. So unfortunately, the person on the left now believes that X is poop, while the person on the right still believes that X is love. And this can be a problem. Not only do they disagree on the value of X now, but because they're disconnected, they may continue moving on with their lives, making more stateful changes that depend upon their assumptions about this variable being shared, even though in fact they disagree on its content. And so as they take consequences of this disagreement, the disagreement becomes more and more entangled and complex. Sometimes people call this the split brain problem, because the two sides of the brain now have gotten very complicated. So how do we avoid this? Well, the classical mechanisms, people like Leslie Lamport developed, consensus protocols, things like Paxos. In the database community, we have kind of conventional wisdom around protocols that arose like two-phase commit. This stuff is tricky, right? This is the stuff that every year when you have to give the lecture, you have to remind yourself how it works so you can give the coherent, cogent lecture to the students so they might have a chance to understand it. All right, but trickiness, that's cool, right? We're all academics. We like things that are complicated and interesting. The thing is, it's not only tricky, it's also bad. This stuff is bad, and you shouldn't use it. But don't just take my word for it. Let's hear what James Hamilton has to say. James, of course, as you know, is a hero of database systems going back a long way, and then one of the architects of the modern cloud. And James was quoted in a report from a conference in 2009. So this is Berman and Chockler's write-up of what James said. And I mean, to me, it's like poetry. And so it's like distributed systems poetry. That's the way I like to format it. So let me read you James's a poem. The first principle of successful scalability is to batter the consistency mechanisms down to a minimum, move them off the critical path, hide them in a rarely visited corner of the system, and then make it as hard as possible for application developers to get permission to use them. So, thank you, Dr. Thank you, Dr. Lamport, for all the Paxos, but really we'd best not use it. So, it's kind of surprising, perhaps, but why is this design philosophy for someone like James? Well, why avoid coordination? First of all, because when you wait for other nodes, when you wait for control from other nodes, you may wait for a very long time. Waiting for control is a bad idea because typically it's a tail latency problem. So you don't get the benefits of smoothing as you scale up. You actually get the downsides of tail latencies as you scale up. So the tail latency of a quorum of machines in a very large system can be very high. This is sometimes known as straggler effects, right? But it's worse than it seems, because if you're waiting on someone else, somebody else might be waiting on you. And so waiting is transitive if you are using waiting, and it leads to slowdown cascades. And so when you are slow, it's not just your problem, it's someone else's problem, particularly in a richly service-oriented environment in a place like Amazon, or in general in building systems in the cloud. Okay, and this is why you don't want your line programmers, even at a place like Amazon, you don't want the base programmers who aren't the super duper experts. You don't want the normal experts calling out to these coordination services, because they will create unexpected slowdown cascades. And where those emerge is in the operations. So someone's going to get a pager call at 2 in the morning that any number of services have failed. And why? It's because somebody down the stack was waiting for somebody else. All right, so how can we avoid coordination? Where is the solution going to come from? Well, traditional distributed systems of the 20th century sort were all about I/O. They were all about mutable variables, whether those variables were database keys or whether those variables were registers in a distributed computer. Almost all our definitions of correctness are about reads and writes of variables. The key is to move up the stack and reason instead about application semantics. So, giving credit where it's due to Peter Bayless, this is his version of a Far Side cartoon. What we say to databases is, okay, database, be good and move one iPhone from inventory to Bob's cart. That's an application level request. But what the database hears is blah, blah, read X, blah, blah, write X, etc., right? We translate rich application logic into a string of reads and writes. And in so doing, we end up having to be very conservative about the values of these reads and writes instead of thinking about, well, what does the application really want? And so most of the solutions that are sort of kitchen wisdom in how to architect good distributed systems are application level semantics. And what we want to do is we want to formalize in some way that's reproducible how to reason about these semantics to get correct applications without paying the cost of coordination. So, Blackboard idea. Suppose you did understand your program semantics. Let's just leap into that future. All right, we'll make the assumption you do understand your program semantics. Which programs that you might want to write actually have a coordination-free implementation? So let's say that those programs are in this green circle. And which programs require coordination? They're outside the green circle. They're the red stuff in the blob of all programs. This is a fundamental question. I want to know, in the green section, I can avoid all this coordination stuff. I can be correct and have James Hamilton's guidelines followed. But for the red stuff, I'm going to have to get permission from somebody to, if I want this program, if the company needs it, I have to get permission from somebody to use the coordination services, right? So this is a classic kind of question of computability. What's computable if I don't give you coordination as a mechanism? And what's computable if I do give you coordination as a mechanism? And can we have a bright line? Can that green circle be crisply defined so that theoretically we understand the class of coordination-free programs? Okay, so that's going to be the next step of the talk. But looking back at what we've got so far in Chapter 2 is we want to try to make autoscaling services stateful, and the key to doing that's going to be to avoid coordination so that they don't delay. And our hope is that semantics of application programs are going to come to our rescue, okay? And that's going to lead us to this question we just asked, which is answered by the Calm theorem. So the Calm theorem started as a conjecture. It's a conjecture that I presented at a PODS keynote a decade ago. And subsequently, Tom Amalut was a graduate student who decided to go ahead and formalize it more crisply and was able to prove it as a theorem. And in fact, had a series of papers that followed on refining definitions of this to get tighter and tighter classes of sort of green circles from the previous slide. So let's look at the theorem. CALM stands for consistency as logical monotonicity. And it says that a distributed program P has a consistent, coordination-free distributed implementation if and only if it's monotonic. So the green circle we saw in the previous slide is the monotonic programs. Those are the programs, those are exactly the programs that can have a coordination-free implementation. Non-monotonic programs cannot have a coordination-free implementation. Okay, in order to really reason about this and to prove it, you need some formal definitions. So the conjecture was really mushy with words like consistency and monotonicity and coordination. Monotonicity, at least, is a familiar concept in logic programming. So database theory, we know this. We can talk about monotone data log, for example. And so programs are expressible in monotone data log. But consistency is not uniquely defined in the literature. And coordination actually isn't really defined at all in the literature. So Tom had to go ahead and put bones behind all this to be able to prove stuff. And I'm not going to go deeply into his theoretical constructs or his proofs, but I will give you sort of a high-level intuition of what's in Tom's work in the Calm theorem. So intuitively, the definition of consistency comes from what was going on in my research group that we sort of passed off to Tom, which is that what we're interested in is program confluence. That is to say that a unique outcome will be guaranteed for the program regardless of any distributed systems networking shenanigans. Things like messages getting reordered, messages getting sent more than once, or issues like computation and message interleavings being non-deterministic. So all those non-determinisms that arise due to asynchrony in distributed systems and retry, all of those non-determinisms do not affect the program outcome. That's what we mean by consistency. And note specifically that it says nothing about consistency being related to the state of variables or reads and writes. It only cares about the outcome of the program. Now for monotonicity, again, this is a standard definition from the literature, although it had to be kind of put into a language and execution framework to be able to do the proofs. But the general idea here is monotonicity on every node in a distributed system says that the set of outcomes from those nodes only grows during execution. So once you know something, once a fact has been derived from a computation or an output has been generated, nothing can happen in subsequent iterations of the execution that will falsify that outcome. And so you can emit outputs in a streaming fashion from a monotone computation without worrying that you'll ever have to retract them. So you can start sending outputs without any regrets. And this is kind of the intuition for why you'd think that the calm theorem might be true, is because if you can emit things without regrets, then you're not waiting to coordinate, right? Okay. And then finally, what is this definition of coordination? This is the trickiest bit, and I think the most insightful thing in the proof of the calm theorem, is to differentiate communication that happens in a computation in order to compute the answer from communication that happens in a distributed protocol that is outside the computation required to compute the answer and is just coordination. So what is this communication that is coordination? And the high-level idea here is that these are the responses that we await in our communication, even though we have all the data required to compute the answer. And so let me give you an illustration of how this all maps onto some examples. So two canonical examples from the database literature that should be familiar to many of us. The first one is going to be distributed deadlock detection, something that's taught in basic classes in databases. And the second is distributed garbage collection in the sense of programming language or persistent objects. Let's do deadlock first. So in a distributed deadlock detector, you have these nodes. Each node's got a waits for graph, right? So the T's are transactions and the edges are waits for edges, but from one transaction waiting for another. And as you're probably familiar with, distributed deadlock detection proceeds by nodes gossiping in some pattern what edges they have. Right, so machine 1 might talk to machine 2, say, what edges do you have? And machine 2 will report back. And machine 1 will quickly see that between machine 1 and machine 2, we see a cycle, a deadlock between T1 and T3. And at that point, machine 1 can autonomously declare that there is a deadlock in the system T1, T3. Note that specifically, there's nothing that machine 3 could say that would falsify machine 1's conclusion. Once machine 1 gets information from machine 2, it knows there's a deadlock. And nothing will change that. Now let's look at a similar problem. So it's again a sort of graph transitive closure problem, but it's a little bit different, which is garbage collection. So in the picture on the bottom right, the circles are objects in a distributed object store. All right. One of the objects is a canonical root object stored on machine 1, and there's references between the objects. So the edges here are pointers, like in a programming language, and the dotted lines are pointers that span machines. Okay, so O1 points to an object on machine 2 called O3, and so on. So if machine 2 gossips to machine 1 all its edges, machine 1 might guess that O5 and O6 are garbage because there's no path from root to O5 or O6 in the edges of machine 1 and machine 2. But what machine 1 doesn't know yet is perhaps machine 3 has an edge or a set of edges that transitively connect root to O5 or to O6. So machine 1 can't declare O5 and O6 garbage until it talks to machine 3. Moreover, imagine there was a machine 4 that had no data on it whatsoever. Machine 1 would still have to ask machine 4 if it had any information that would falsify the assumption that O5 and O6 are garbage. And so this protocol for garbage collection seems to require talking to all the machines, even if all the data is in one place. And this is what we're going to call coordination. This is the kind of stuff we'd like to avoid. Unfortunately, we can't avoid it for garbage collection. And the nice thing about these examples is they're so clearly monotone and non-monotone. Distributed deadlock is about the existence of a waits for cycle. So existence is a monotone property, and like literally syntactically, there exists is an easy thing to look for in a logic program. Garbage collection is the non-existence of a path from root. Not exist is clearly non-monotone. It's a negation. And so again, syntactically, if you write down garbage collection as a logic statement in either first-order logic or data log or SQL for that matter, you can syntactically see that it's using a non-monotone construct, not exists. Okay, so hopefully this gives you some intuition as to the coordination that we felt like we needed for garbage collection is precisely because of its non-monotone nature. This issue of proving that there does not exist a path requires you to ask everybody, does there exist a path? Right? Whereas the existential monotone test for distributed deadlock can be answered incrementally in a streaming fashion without coordination. Okay, so maybe you think that's interesting, maybe you don't. I think it's pretty cool, but kind of who cares, right? Theory's theory. Well, no, actually theory can inspire practice. So one of the things that's been going on in our group is that we've used this kind of calm thinking to inspire architectures for systems that are extremely fast and also scalable in a really unique auto-scaling way for the cloud. Because when you have no coordination in your system, when you really design so that threads never have to talk to each other on the fast path, they just gossip in the background, then you can get crazy parallelism. It's like shared nothing with no coordination. And you also get very smooth scalability because adding nodes, adding threads, whatever you add, doesn't require any additional coordination during the fast path. So we'll see this in the ANA key value store I'll describe in a few slides. Another thing that's kind of interesting about the calm theorem is that in an appropriate language, in a language where you're using logic in a very clear way, you can actually check for monotonicity syntactically. As we saw in the previous slide, exists versus not exists, right? So if you're programming in SQL, it's very easy to see the monotone constructs like joins and selections and projections, and the non-monotone constructs like not exists or except. If you use a distributed programming language that is logic-based, like the one we designed called Bloom, you have a similar power to syntactically check for monotonicity very easily. Okay, but Bloom hasn't taken over the world. Who writes distributed programs in logic? Well, that's an open question. As of now, people only write distributed programs in sequential languages like Java for the most part. So it's an open question how we'll write distributed programs. Maybe a logic style language will be the answer here. Another possibility that I'll talk about later in the talk is maybe logic is the internal representation. It's sort of the compiler's language, and that we'll have other languages that are maybe more familiar or more programmer friendly above it, but will compile down to logic so we can do our analyses and our optimizations in the way that we think about in database systems. So I'll talk about that later in the talk. A final note about the calm theorem is that the calm theorem explains Eric Brewer's CAP theorem. And particularly, it tells us the opportunities when we can have all our cake and eat it too, so to speak. We can have safety and liveness, consistency, availability, and partition tolerance all at once. And this is a conversation for another day. I will point out that Peter Alvaro and I have written a short article on the calm theorem that's going to appear in CACM later this year. And so if you want a recap of this discussion with more detail, pointers to the literature, and then some discussion of things like how calm relates to CAP, you can look forward to that paper, or here is a link to it in archive. Okay, so the calm theorem introduced this idea that monotonicity is this bright line between what can and cannot be done coordination-free. And that takes us then to the last chapter of the talk, which is about what we're building at Berkeley based on these understandings in terms of how do you get stateful serverless computing to work, and how can we make cloud programming more real. And the Hydro project is sort of our umbrella for exploring these questions. So here's a block diagram architecture of Hydro. It's an ambitious project. It's a big system. It's got multiple components. The ones in dotted lines don't exist yet, and the ones in the solid boxes do. So at the base is ANA, which is an auto-scaling and multi-tiered key value store that offers fairly strong consistency, but is still coordination-free. So there's been a couple papers on that I'll refer you to. And then above that, we have our own functions as a service system, which is stateful. So it allows functions to maintain state in ANA at very low latency using caches. You see the $ there. So there's caching very close to the function executors, which makes for very low latency I/O and allows the functions to be stateful. So actually, there's been papers on aspects of Cloudburst that are accepted to SIGMOD this year, as well as to Eurosys this year. And I'll point those out as we go through the discussion. An overview of Cloudburst is in this archive paper that's linked here. And then finally, hydrologic and hydrolysis. So hydrologic is this idea that a logic language could be the internal representation, the IR, for a cloud system. And so we call this a disorderly IR. That's language we used in Calm because it's not sensitive to the order of these actions that may be non-deterministic. And then finally, above hydrologic, we're envisioning, and this is work I'm going to kick off with Alvin Chung, my new colleague at Berkeley, who's more of a languages person, to try to compile from multiple different distributed programming metaphors, some of which are new, like Bloom, some of which are more familiar, like functional reactive programming in RX, actors in Akka or Orleans, futures in Ray. So there may be many such programming models. Can we have a way to compile them down to an internal representation of logic, like hydrologic, so that we can play the games around coordination avoidance, around locality and data placement, around data flow and query optimization? Can we use those games to do the coarse grain optimization of these programs across machines? Okay, so that's kind of the big picture of Hydro. And what I'm going to do for the rest of today is talk to you a bit about Anna and Cloudburst and how they've built up from the state of serverless today to something that's quite a bit richer. So Anna is a serverless key value store, and our goal with Anna is to make it work at any scale. You know, there's this Jeff Dean quote that says every time a system gets 10x bigger, you have to re-architect it. Now that's clearly not a lesson for the modern 21st century cloud, right? We need systems that'll scale up and scale down smoothly. You can't have a different system kick off at every scale point. And so what we want is a single key value store that on a single node will be just as fast as the fastest single node in-memory key value stores like Redis. But if you need it to scale up, it should scale as large as the largest cloud-based storage systems like S3, while retaining that Redis-style performance at that scale. All right, and the way we achieve this is coordination freeness. We use the CALM principle to design consistency levels for your reads and writes that don't require coordination. And we do this using simple lattices and compositions of these very simple lattices into richer metadata around your keys. And this is something that I won't have time to talk about today. You can read about it in the paper. So that's in the ICDE paper. In the VLDB paper, we talk about then how we not only auto-scale this system, so it responds to workloads and creates replicas corresponding to the amount of work that comes in, but it's also multi-tier so that you can have a memory tier of Anna sitting over a disk tier of Anna, and then you basically can have data move up and down the way we used to do with buffer pools between these different tiers of the key value store. And you know, my students won Best of Conference awards for both these papers, so real proud of them and can't help but brag a little bit about their work. So some quick graphs from the papers on Anna's performance. This idea of any scale. So what you're seeing here is we're adding threads to an Anna server, and we're seeing the maximum throughput of the system go up. Notice how smooth this curve is. So every plus is adding another core to the system, essentially by adding another thread. And the transitions of colors are when we go from one machine in the cloud to two machines in the cloud. So these are 32 core machines to 3 machines in the cloud and so on. And you'll see that, you know, there's the tiniest of blips when we go from 1 to 2, where we just are beginning to see the cost of just networking. But beyond that, this thing is scaling very, very smoothly. And it will continue to do this as we go to more machines and even across the cloud. So this kind of smooth scalings is made possible by the fact that every core is just doing its own thing and there's a minimum of coordination. And one of the things that's really remarkable about this is because there's no coordination, under contention, when you have hot keys that are getting lots of writes, Anna will continue to perform super fast where other systems will slow down due to contention. All right, so mass tree is probably the fastest key value store for memory that's come out of research. It's Eddie Kohler's work at Harvard. And then TBB is the Intel Thread Building Block Hash Table, which is, you know, the standard multi-core hash table implementation. Under contention, Anna is 700 times faster than both of those in terms of throughput. And in a geo-distributed environment, it's 10x faster than Cassandra as well. Okay, so because we're not doing coordination, we can go really fast. And to put some numbers behind that, look at how time is spent under contention in Anna versus in TBB or mass tree. Anna's spending 90+% of its time servicing writes and reads. And the other systems are spending 90+% of their time coordinating. Okay, and then in terms of auto-scaling, very quickly, this is the VLDB paper of last year. On the left, we're seeing that as throughput increases because workload increases, the cost curve for the system kind of hugs the performance. And this is what you want out of an auto-scaling system, is that at a sort of fine grain, you want costs to correspond to throughput. All right, so it's the red dotted line hugging the blue line. That's the key to the leftmost chart. In the upper right, what we're showing you is that you can make trade-offs between latency and cost, depending on how you want to configure the system. And this has to do with how you do your tiering. So if you want to have more memory tier than disk tier, you can pay for more performance by having a multi-tier system. And then the key sort of takeaway in terms of performance at the bottom is that for the same price, you can get 350x the performance of DynamoDB using ANA, because it is multi-tiered, and you can have a small memory tier serving hot data and a large disk tier that doesn't. And we still get very rich consistency relative to the partitioned DynamoDB, which actually doesn't offer very strong consistency. So the next thing I want to talk about are some applications that some students at Berkeley have built and postdocs on top of Cloudburst. It's been really great having people building applications on the platform. I highly recommend it for your research. It really drives out some of the scaling issues and paths through the code that you didn't expect, some of the tricky details that you wouldn't have thought of, and it's starting to inspire the research as well. So we've had 3 classes of applications built on top of Cloudburst. I'll show you serverless data science in the form of Jupyter notebooks, work that Charles Lin did. I will show you robot motion planning, which was led by a postdoc in our robotics group, Jeffrey Iknovsky. And I won't, unfortunately, get time to show you ModelZoo, which is a hosted prediction serving environment. So I'll just briefly show you the user interface of ModelZoo. It's built by a bunch of undergrads at Berkeley. They're hosting models that have been trained on standard corpora of data like ImageNet, and you can go ahead and fire up one of these models and then use it. So for example, you can upload a picture and find out if there's a cat in it and so on. And this is all auto-scaling, so when it's working, it's using Cloudburst resources, and when it's not working, it's not using any resources. But what I want to focus on first is a demo of Serverless Jupyter. So why would you want to have Jupyter notebooks, which are client desktop applications, hosted in a serverless environment? Well, at Berkeley, we have large deployments of Jupyter for our courses. There's a picture here of Data 8, which is our massive Introduction to Data Science course. It's taught in the concert hall when we're allowed to get together at Berkeley. Overall at Berkeley, we have 37,000 students using hosted Jupyter notebooks on campus at any given time, using the Jupyter Hub backend that comes with Jupyter. And there's significant resources allocated to this, and it faces scaling issues and, of course, resource efficiency issues, because a lot of the time these Jupyter notebooks are sitting idle, but they're holding on to compute in the cloud. So Jupyter on Cloudburst is a prototype notebook. It's been ported to run on Cloudburst. Each cell, when you run it, is a serverless function execution. So when you hit return, a function is spawned in the cloud to run that cell. And the reason this works is because the state of the notebook is being stored in the cloud in ANA. When a notebook is not running a cell, it holds 0 provisioned compute. So basically, when you hit return in a cell, it causes a Lambda to fire up in Cloudburst. And if that cell assigns a variable in Python, then that variable is stored in ANA. So the program state's stored in ANA, and then each cell, when it does reads, is going to retrieve only the definitions it needs. So it will only look at state it's dependent upon. So let me show you a demo of this. So what you're going to see in this demo is a standard Jupyter notebook, but remember, each cell is running in a separate Lambda. And as we assign values to variables, remember that the machines we're running on are different in every cell. The IP address is different, but the variables are being persisted in ANA across those cell invocations. And you'll see from a user experience, it looks just like a regular Jupyter notebook. Now, beyond the operational benefits that we just saw, this serverless architecture does more than just address the scaling and cost problems. It also enables new research directions. One of which, for example, is a larger aggregate memory. So for example, if you spike memory usage in a Jupyter notebook, you simply crash. But in Cloudburst, there's the opportunity for each cell to have its own memory. And what we're doing now is we're going to fire off a whole bunch of work on Cloudburst, and then we're going to fire the same bunch of work off on the Berkeley Data Hub, which is the standard Berkeley campus infrastructure for hosting notebooks. So we're running this code on both Cloudburst and Data Hub. And what you're going to see is that on Data Hub, allocating all these giant arrays is going to cause the Python kernel to blow up. It allocates too much memory and it dies. But when we go back to Cloudburst, what we're going to see, and it takes a little while to finish computing because it's got to allocate all these arrays, every cell's on a different machine. So we now have the aggregate memory across all those machines, and it runs to completion. So we have a number of other things we're pursuing, and in future work we'd like to have each cell run on a different class of hardware if we want. That's possible because we've decoupled each cell as a separate computation. So say machine learning code could run on a GPU, whereas other things could run on a cheaper CPU. We want to be able to have asynchronous fetching of data, for example, or generally asynchronous tasks. Again, possible because the cells are decoupled from each other. And then the idea in these times when we're remote that we should be able to have notebook sharing in the cloud, not just sharing of the text of the notebook, actually sharing the state of the computations in the notebook, which when you think about big machine learning models is really actually quite a compelling scenario. So the next demo I'm going to show you is serverless robot motion planning using Cloudburst and Anna. So robots, when they navigate, they need to find a shortest path from a start to a destination, and that's a kind of tree search problem, often using random search. And to speed it up, a standard technique is parallelism, where each searcher is doing random search, but they're sharing short paths when they find a good path, so that the random explorations can be shared across these things. So this is a visualization of 3 AWS Lambda functions simultaneously running a motion planner to navigate a two-dimensional space. Now, there's different compute requirements for navigating in 2D, like go to an office desk on the left, and navigating in 8D, where you're dealing with all of the rotations of the joints in the robot. So it's a high-dimensional design space of how to move those arms. And as you can see over time, there's simple planning problems about navigating the space and occasional bursts of complex planning problems around doing things like grasping. And that's why serverless computing is attractive in this setting. So what we would like to do is very quickly launch hundreds of functions in the cloud and have those functions share data in the way we saw in the visualization before. And then we're going to need some kind of conflict resolution between these things. So we need a data consistency model to merge the findings of these different lambdas. And as we spoke about, standard cloud functions don't share state whatsoever because they have no communication and only high latency access to storage. So when the robotics team at Berkeley tried to build this, they couldn't build it on vanilla Lambda. Instead, what they had to do was, after they would launch their Lambdas, to get them to communicate, they would have to have a standing non-serverless coordinator node reserved in the cloud, whose job was simply to hear messages from these guys and route them back to the people that needed to talk to each other. And this sort of coordination node became a bottleneck in their execution, which is why they came to talk to us. And so instead, they're now using they're now using Anna, and they can have as many Anna nodes as they need to scale up their number of Lambdas. And those Annas do that conflict resolution, that merging, using lattices designed by the robotics team on the fly to merge things in the background. And so then they can scale up from many Lambdas communicating together, as you see this illustration, to a really big search space with lots of Lambdas that snap in quite fast. So you can ask, how much benefit do you get from this parallelism? Well, here's a graph running on Cloudburst. At the bottom, we see the path quality, or the path length, of running 100 concurrent Cloudburst functions. At the top, we see the path length of 10 concurrent Cloudburst functions. And you can see that the cost with 10 functions after 60 seconds on the far right, if you trace that back to the left, is what you get with 100 concurrent Cloudburst functions in 2 seconds. All right, and this is real world stuff, so we want it to happen in real time. So the difference between 60 seconds and 2 seconds is a big deal. So here's an example of the robot. It needs to grasp this bottle. So let's watch it doing that with 10 executors, 100 executor, and a single executor. And you can see the single executor is making no progress whatsoever. It's just thinking right now. The 100 executor instance, this is running in real time on a real robot with the real implementation on Cloudburst, finishes just then. And the 10 executor is kind of going to poke around for a while longer till it gets it right, and then eventually it's going to catch up. Okay, so that was a little example live of robots running on serverless stateful functions as a service. Okay, so this closes out the 4th chapter of the talk. We talked about Anna as a calm, any-scale key value store, multi-tiered as well. We talked about stateful functions as a service and the Cloudburst implementation, and the opportunity of putting caches close to your functions while still having a decoupling between compute and storage and scaling them independently. This raises challenges in cache consistency, which are addressed in a couple of papers that we've written this year, and there's more work to be done there. And then we talked about some stateful Faas applications as well. So did we answer the big question of how we're going to program the cloud? Well, not yet, I would say. We're certainly pushing the state of the art in functions as a service in my group, and we'd like to go beyond that to this bigger question. Because stateful Faas is really a fairly limited API. This is kind of baby steps for cloud programming. It's still a sequential programming model of individual functions. Programmers are responsible to think about all of the stuff, because there's no contract from a language like Python about distributed properties. The developer has to reason about distributed consistency in functions as a service. They have to decide if they need to coordinate. There's really none of the benefits that we talked about wanting from a richer programming language. So all we've done is shown that you can get stateful functions as a service, but some of the work we did previously on Bloom needs to be brought into this context to get richer things. So the real dream is going to take time. And as I said, there's this hydrologic and hydrolysis layers of hydro are the next stage of the research that are going to explore some of these stateful programming problems, logic programming problems. Again, very much in the wheelhouse of our community because of opportunities for query optimization, opportunities for exploiting logic programming, all kinds of things that we are the experts on in the computer science community. So I encourage folks to think about these challenges of distributed stateful computing as being very much data engineering problems or database problems that we all can look at. So to close out, my key collaborators in this last sort of few years of this work on serverless computing and data have been my graduate students Chingang Wu, Vikram Srikanti, and Charles Lin, and Johan Schleier-Smith, and then close collaboration with my colleague Joey Gonzalez. If you're interested in the systems I talked about today, Anna, Cloudburst, Hydro in general, Aft, all that stuff is in the Hydro repo on GitHub here in the first link. The Bloom language is still running, it still works. It's up at bloomlang.net. I have students still using it, and I expect it'll get a revisit and refresh in the context of hydrologic over the next year or two. And then finally, all this work is done under the auspices of Berkeley's RISE Lab, of which I'm a co-director, and there's many things going on in the RISE Lab. There's a whole raft of faculty and dozens of graduate students that you can learn about at the link down there. And so with that, thanks very much for having me. It's been almost as much fun as being in person, certainly not as much fun. I hope I can interact with some of you on some of these research topics in a deeper way sometime soon.
Thanks, Joe, for this. Sorry, let me open my video as well. Thanks, Joe, for this great talk. We have a couple of questions. I'll start reading them on the Q&A. Joe, if you can turn on your camera. Yes, you did. That's good. So I'll start with the questions on the Q&A window. And if for the others who are still listening, please do ask your questions using the Q&A button.
Why don't we... There are also some questions on chat, I noticed.
Yes, I saw that some of them are there. I'll ask them as well. So the first question is, I think, more clarification question. That's the reason I will go with that. Koreharu Kurohara asked, in the first chapter, what is the point of comparing serverless computing and distributed computing? I guess his point is that aren't they super different, or what? So a clarification, I guess.
Yeah, happy to talk to that. Can you guys hear me okay?
Yeah.
Yeah, I mean, serverless computing is, it's an example of distributed computing. The idea with serverless computing is that you can get access to an auto-scaling system made up of many computers in the cloud that has access to shared storage that is as big as the cloud. And so, the model of serverless is not that I can give you a laptop in the sky, it's that I can give you access to the cloud, and the cloud is a distributed computer. So serverless is an instance of distributed computing, and arguably it is the future of distributed computing because nobody really wants to configure distributed computers. That's too hard. We're going to be programming in some model that feels like serverless.
Okay. The second question is, Animal Hack asked, why aren't we exploring Prolog, Datalog, or their extensions, even answer-set programming for the logic programming part of your vision, I guess?
Yes, that's a wonderful question because that's exactly what we have been doing. So languages from my group like Bloom are deeply seated in Datalog. Bloom is based on a logic programming language called Daedalus, which is a stateful temporal extension to Datalog. And we're leaning on decades of research from the pods community and the data log community in the large in the design of languages like Bloom. And I believe that data log is really foundational to the future of distributed programming. So we've been exploiting that. That keynote that I gave at Pods in 2010 said exactly this point. And so I'm delighted that you brought it up, which is that I think the data log community has much to offer to distributed systems and distributed programming.
Okay, I'm asking from the panelists and the chat window as well. So what level of consistency does Anna provide for these performance results? It was asked by Kozami Doji. Sorry for.
Yeah, I believe we used the strongest level of consistency at that time in the implementation, which was causal consistency. So that's one of the strongest consistency levels you can get on single key access is causal consistency. There was work by Peter Bayless, Alan Feketa, myself, and others kind of laying out what are the consistency levels for read-write consistency that you can expect with coordination freeness and causal sort of at the top of that hierarchy. So we tried to be as consistent as one possibly can.
Mm-hmm. I'm going to the Q&A part now. So I'm asking one from Q&A, one from the panel window, chat window. Because coordination-free may be under-controlled, is it possible that coordination-free computation incurs extensive, large amount of useless communication? Is it possible that coordination-free computation results in lower performance than a carefully coordinated computation?
It's a very insightful question. It's a hard one to answer. I think it's a great theory question. So what, like a lot of computability, right, you could have a polynomial time algorithm that runs more slowly than an exponential algorithm for certain problem instances, right? So again, here you can have a coordination-free implementation that might run more slowly than a coordination-full one for some problem instances and configurations. And so one might want to ask questions that are, more interested in constant factors to try to figure this out. What's the real cost of coordination in my deployment? How much extra communication does my implementation do? And then refined questions about communication complexity, not just coordination complexity in that lens. So I think that's an excellent question, and it's not one with a simple answer. You really have to look at your problem instances and your configurations. So thanks for asking that. That's very
insightful. I forgot to mention the question was from Yan Fang from Northeastern University. The next question is from Sudarshan. Sudarshan, would you like to unmute yourself and ask if you want? So we have a live thing. Yeah, go ahead, Sudarshan.
So the question is, it's very nice when an application satisfies some of the monotonicity properties that Calm needs. But if you go to a typical, web application that people want to build, how amenable are these to really satisfying these monotonicity properties? Or is it that a significant chunk of it is non-monotonic and therefore we are stuck?
Great question. So I guess to answer it, I'll point you to papers by people like Pat Helland that have been coming out. There's sort of papers on good design patterns for distributed programming. And one of these was very much an inspiration to our work on Bloom a decade ago. It's a paper called Building on Quicksand. And in that paper, he and Dave Campbell, who was very involved in SQL Server and Microsoft's cloud computing, they talk about how they built applications to avoid coordination bottlenecks. And if you sort of unpack what they're talking about, it's that they're using monotone design patterns at the application level to achieve things like shopping carts for Amazon, to achieve things like, what do you do if it turns out that inventory runs out when somebody makes an order and you've told them that you will ship them the order? And so looking into those real world examples was exactly what motivated our research, in fact. One other place to look for, and there's many, but one that's on my mind because we taught it in my grad class yesterday, to look for more real world examples is Amazon's Aurora database. So there's some nice papers from our community on Aurora. One of the recent papers talks about how they avoid coordination in Aurora. And mostly what they talk about is a design pattern in which they're using monotonically increasing log entries like epic numbers and other things that can be generated without coordination, if you do it cleverly, to achieve a coordination-free sort of, it's not quite transactional, frankly, but near transactional database system that scales up very smoothly. So there's lots of, I would say, both application level and system level reason to believe this is quite practical. And we've been building things, as you saw as well, to help validate.
So I guess last two questions due to time. Gustavo Alonso asked, does adding state to the function changes anything in the nature of the functions themselves, their cost, implementation, etc.? If not, why not?
Well, if you're looking at the commercial offerings like Lambda or Google Cloud Functions, it changes a lot because it forces you to make round-trip calls to their scalable I/O systems, which are just amazingly slow, incredibly slow. And so you have to start thinking about how can I possibly do things without memory, which often you can't. I would say in Cloudburst, it's really not a big deal to add statefulness to your functions. You know, the memory references in your program are handled by an in-memory cache that's sitting on the same computer as your computation. And so you can sort of reference state and memory without worrying about cost. You're still in this realm, though, where you might want to think about things like, is my program monotonic or does it need coordination? And so I think those deeper questions do come out once you start looking at distributed state in general.
Okay.
And I'll make one more brief point. I think, you know, Gustavo deserves this as well, which is a design pattern, which is a good one that's common in distributed programming, is to use immutable variables. So try to program without ever changing the state of a variable once it's been set. Immutability is monotonicity for beginners. It's a monotonicity of simply going from unset to set and then never changing it. You can use richer things than immutability. You can use truly monotone types of computation as well.
I will combine these two questions. Basically, I guess with this FAS and your system, can you support SQL-like queries? And what are the key challenges in supporting these type of queries?
Yeah, so one of my students that was on that last slide, Johan Schleiersmith, has been working on building a storage backend that you can run SQLite in a cloud function. And that work has been discussed at venues like HPTS, but there hasn't been a full paper on it. You have to give up on serializable transactions, as most of the cloud vendors' databases do. So you don't get serializable transactions from Aurora either. But if you're willing to deal with things like repeatable read or read atomic consistency, then you can imagine and indeed implement SQL in a function. I haven't seen yet an implementation of a full partition parallel SQL system. There's a paper, though, out of MIT this year for read-only SQL queries in serverless that I'd refer you to, using plain old Amazon Lambda, because read-only things are relatively easy in stateless serverless functions.
Okay, I think the last question I'll let Dimitris ask directly. Dimitris, unmute yourself and ask, please.
Oh, I'm sorry. Basically, I wanted to ask you about this example about you're searching the space. If you have a completely, if you don't have any coordination, how do you know you actually finished the search? I mean, it's a little, is it like everybody has to keep, I mean, there must be levels of coordination there. I mean, what exactly is coordination that you allow? Or...
Yeah, so there's a more general version of your question, which I'll just generalize up from the robotics example to any general computation. How do you know when you're done in a monotone coordination-free programming model? How do you know there isn't going to be a better answer if you wait longer? And the answer to that typically is some sort of threshold computation. So if you think about an SQL query, you know, is the count of the table greater than 10? That's something that you can give a Boolean yes/no answer to after you've counted 10 or more things. And you don't have to wait to count all the things because you've put in a threshold. So typically when you're programming in a monotonic environment, you have some kind of threshold test at which you produce an output. And you can program those threshold tests in a monotone way, like the threshold of going from less than 10 to greater than 10 is something that you can observe coordination free. If you can't come up with a threshold test, then it's, in essence, you're asking for coordination. And so it's sort of part of the problem statement or the program spec to make sure that there's some kind of threshold test for completion. And in the case of the robot, it's very simple. It's, have I arrived at the destination, right, in a bounded amount of time.
Okay. Thank you so much for Joe for answering, great talk and answering all the questions. In the interest of time, we have to stop here.
So why don't we give Joe a hand?
We will do a virtual one. Thank you so much for the great keynote talk. So, but I would like to mention that we have a Slack channel. So hopefully, if you have more comments, maybe you can ask there. And Joe, if you have time, maybe you can check the Slack channel and follow up there. There were some more other questions. Before we finish this session, I would like to make a couple of announcements. We will continue with many sessions today. Please look at the program and Zoom links there and attend those sessions. Tomorrow, we will have a keynote talk again, the last keynote talk by Vipin Kumar. And we will have an award session that will give 3 awards. So one is Rising Star, the other one is 10-Year Influential Paper Award, and the IEEE Computer Society Award. I won't tell who are the winners, so surprise, surprise. So please come and join those talks tomorrow as well. All of the links and everything is available on the registrant's website, Zoom links, and the Slack links as well. So thank you again for attending this great keynote talk and your questions and participation. So hope to see you in the other sessions as well. Thanks, and thank you again, Joe. Okay, so we are closing this session now. Thank you.